Okay, now let's talk about some applications of Bernoulli's equation. So first we have in this figure here, we'll say in figure A first, we have a wing of an airplane. Okay, so an airfoil here. And first off, I want to point out that the height difference in this airfoil, difference between there and there, or any 2 points, or even if we take between these points here, the entire thing. This is very very small. If we're talking about like the plane, wing, and it's probably less than a meter, right? So yeah, the pressure difference created just by this height here is going to be very small. And so when we write out Bernoulli's equation, which is pressure 1 plus rho g y1 plus 1/2 rho v1 squared is equal to a constant. This isn't going to play a large role. This height difference isn't going to play a large role, and so we're going to kind of just ignore that one for here. And when we look at this, we can see there the wing is designed, a couple different ways. It's kind of slanted down a little bit here. You see it's slanted down, and then it's also a little bit longer. It's curved here on the top. And so it's designed, and there's a lot of aerodynamics and going on and design of this, but it's designed in a way that it causes the air to flow a little bit faster over the top. Okay, so we have kind of the velocity on the top is greater than the velocity on the bottom. Okay, so if we have the velocity on the top greater, and so basically we have Bernoulli's equation becomes pressure plus 1/2 rho v1 squared as a constant, right? And so we have kind of this on the top and we have it on the bottom. If the greater velocity we have, if we have a greater velocity, this term goes up, and if the whole thing has to remain constant, then the pressure must go down, right? So the faster the wind speed, the lower the pressure. And if we design this so that the wind speed is faster over the top, it means that the pressure is going to be less on the top. And so, we can have, like, we see this here, pressure on the top is that, and pressure on the bottom is a little bit longer arrow here. I'll emphasize this. Pressure on the top is kind of small, pressure on the bottom is much bigger. And we know that, a force is equal to a pressure times an area, right? So if you get a pressure difference, the areas are roughly the same there, maybe slightly bigger area on the top. But if force is a pressure times an area, if I have a pressure difference, I'm going to have a force difference, right? And so this pressure difference created here causes a net force, which is upwards. And this is a part of the way that we get aerodynamic lift. So aerodynamic lift is caused, at least in part, due to Bernoulli's equation and just the difference in air speeds over the top. The slower it travels, the greater the pressure. You can think of it in terms of energy. That if the air isn't moving a whole lot, not a lot of energy is going into moving it, so more energy can be used to kind of do work in the form of pressure. So the slower it moves, the greater the pressure. The faster it moves, the less pressure. Now there's also a little bit more to this. It's not just Bernoulli's equation. It's a little bit more complicated than this. We also have, as particles come in here, and this isn't quite so much related to this video, but it is stuff that we've seen before. As particles come in, then they hit here and they have to be deflected down. And so we can actually use conservation of momentum to discuss this as well. Because, if this is being deflected downwards, then momentum must be conserved. So there has to be something going upwards, right? Or even, you can look at it in the terms of Newton's third law with action reaction, right? The wing is pushing the particle down, and so then the particle must push the wing upwards. So there's that going on as well because of the deflection. So it's actually, there's a couple things playing a role there, but I wanted this video to focus mostly on just how Bernoulli's equation adds to aerodynamic lift. And we can see a similar thing if you have like a sailboat and you have your sail is right here. The sail is designed in a way so that over this side of it here, you can get a faster airflow. On this side here, and so you reduce the pressure, and there's a greater pressure on the back, and you get it moving forward. So you can actually see, it can be designed in a way, and if you've ever been sailing or anything, the wind can be going this direction, but you can actually be sailing into the wind because of the way that this sail has been designed to kind of get a pressure difference there to give you a net force forward. Another example that we can take a look at is maybe when you're driving along the freeway, you might be driving next to a large truck or another car, and you notice it feels like there's something pushing you towards that truck or that car. So we have that situation here. Now, consider the car is moving this direction to the left, so is the truck. And as these two vehicles move, there is air that is coming in this way, and half this air must come down below the truck, and half the air must come up over the car here. And so there's going to be effectively twice as much air flowing in between these two cars as there was if the car was by itself. So we have this increase in airflow between the two vehicles. So because there's more air actually flowing through, we're again going to have it flow much faster via the continuity principle again. And so the air, and you can see this again from these streamlines, the air is traveling much, much faster in the middle between these two vehicles. So from what we know about Bernoulli's equation, if it's the faster the air is moving, the lower the pressure. Now you might feel like you're pulled in to the side when you get next to the truck, but that's actually not true. When the velocity is greater in the middle, the pressure is reduced, yet the pressure on the outside remains the same. So what's actually happening is that you are being pushed inwards. You have a decrease in pressure and therefore a decrease in the force acting on the car outwards, and the pressure remains the same, pushing it inwards. So both the car and the truck feel forces. Again, we have a force is pressure times area that are pushing them towards each other. So again, another consequence of Bernoulli's equation. Lastly, let's take a look at a dam and see if we can find the velocity as water exits the puka there. So a couple things with this figure. We have here's the top of the dam up here, and we'll call this area 1. And then as it comes out over here, we'll call this area 2. So we'll say here also that this is where height is equal to 0 for simplicity. So the height up here at height 1 is just h. We'll also say the pressure up here is 1 atmosphere. So pressure 1 is 1 atmosphere. And pressure 2, this is just as the water exits the dam. And so the pressure that was over the top due to the water is not there anymore. The only pressure over the top of it is just atmospheric pressure plus the increase due to the weight of this air column above. But that's very small. The density of air is roughly 1 kilogram per cubic meter, so it's pretty small. So we'll say actually pressure 2 is also equal to 1 atmosphere. So pressure 1 will equal pressure 2. They're both on the outside. They're both approximately 1 atmosphere. So area 1 at the top of the dam is much greater than area 2. Then by the continuity equation, we can say that velocity 1 is going to be much less than velocity 2. which makes sense. Velocity 1 is the rate at which water is dropping behind the dam, and velocity 2 is the rate at which is coming out of the puka at the bottom there. So velocity 1 is very small. In fact, we can say that velocity 1, we'll simplify this a little bit and say the velocity 1 is equal to 0. Which, if you ever looked at the top of a dam, you really can't tell how quickly the water level behind it is dropping. So saying velocity 1 equals 0 is a fairly reasonable assumption. So velocity 1 equals 0. We'll say height 1, or actually y1 is equal to h. y2 is equal to 0. And this is just based off of where we set our datum. And we'll say that pressure 1 is equal to pressure 2, which is equal to 1 atmosphere. And now we'll write out Bernoulli's equation and see, with these assumptions here, what we get out of it. So with pressure 1 plus density times gravity times height 1 plus 1/2 density times velocity 1 squared equals pressure 2 plus density times gravity times height 2 plus 1/2 density times velocity 2 squared. And so since pressure 1 is equal to pressure 2, these will cancel out. And since y2 is equal to 0, this term is also gone. This is 0 here. And velocity 1, we also said velocity 1 was equal to 0, so this is also equal to 0. So a lot of these terms disappeared from our assumptions. And what we're left with is that we have density times gravity, and y1 we said was the height, so rho gh will be equal to 1/2 rho v2 squared. In solving this, we have the densities will cancel out. And solving this, we will have v2 is equal to the square root of 2gh. So the speed at which water exits the dam, at the bottom of the dam, is the square root of 2 times gravity times the height of the dam, the height difference between the puka and the top of the water level. This is the same conclusion that we came to both in kinematics as well as energy, when we considered a ball dropping off a certain height, and we neglected friction, we neglected wind resistance, and also notice there we also neglected pressure differences between the top up here and the bottom. We actually said that P1 and P2 were equal to each other. That was something we did, which is what we did in this case as well. And we ended up saying that the speed, if this started out, if v0 was equal to 0, we said that velocity out here was equal to square root of 2gh. We also came to the same conclusion with conservation of energy, neglecting wind resistance and pressure differences. So this is the same conclusion that we came up with previously, like dropping a ball off a cliff. Same thing works for pressure being, or for water coming out of the bottom of a dam.